everyone, thank you so much for joining the video. Today we're going to be looking at the ionic product of water, Kw, and here are our learning objectives. So the first is to know that water is slightly dissociated, and then to derive Kw from the equilibrium constant for this dissociation of water, and to know that Kw varies with temperature. We'll then be able to use Kw to calculate the pH of a strong base from its concentration. Now we're going to discuss what the ionic product of water is. So water is actually slightly dissociated, and so this means that it can act as an acid or a base depending on the nature of the system. And this kind of behaviour we call amphoteric behaviour. So in this example we have two waters which are reacting together, and they form the hydroxonium ion and the OH- ion. So we see that one of the waters is acting as an acid because it's donating a proton, and the other one is acting as a base because it's accepting that proton. And if we think back to equilibrium constants, if we try and find the equilibrium constant Kc of this equilibrium, so Kc is equal to the concentration of the products at equilibrium over the concentration of the reactants at equilibrium. And so that means that the Kc for this equilibrium equals the concentration of H3O plus ions multiplied by the concentration of OH minus ions over the concentration of H2O, and that'll be squared because we have two of them. However, the concentration of water is actually a constant, and so we can include this into the overall equilibrium constant. And so rearranging this, we have Kc multiplied by the concentration of water squared is equal to the concentration of H3O plus multiplied by the concentration of OH minus. And we call this new constant Kw, and this is the ionic product of water. So we have that Kw is equal to the concentration of this H3O plus ion multiplied by the OH minus ion. We can also write this as Kw is equal to the H plus ion multiplied by the OH minus ion. So like all equilibrium constants, temperature affects the Kw. And so if we have a look at this equilibrium, we have water, which is in equilibrium with its dissociated ions, H plus and OH minus. And from this equation, we can tell that the forward reaction is endothermic, so it has a positive enthalpy change. And this is because bonds are being broken, and that requires energy. And so the reaction is endothermic. And that means that the backward reaction is exothermic, so it has a negative enthalpy change. And so now let's think about what would happen if we increase the temperature. So if we increase the temperature, I'm going to call the temperature T. If we increase the temperature, then the equilibrium will move to decrease the temperature. And so it would favour the endothermic reaction. And so that means that it would favour the forward reaction. So the equilibrium favours the forward reaction. And so that means that more products would be formed. So more of the OH minus and H plus ions would be formed. And so thinking back to our equation for Kw, we have Kw is equal to the concentration of H plus ions multiplied by the concentration of OH minus ions. And so if we've got more of these products, that means that our value of Kw will be a lot bigger. So in conclusion, if we increase the temperature, then Kw will also increase. And then secondly, if we decrease the temperature, the opposite will happen. So when we decrease the temperature, the equilibrium favours the the reaction that will increase the temperature. And so the equilibrium shifts to the left and favours the backward reaction. And so there are more of the reactant formed, so the water. And so that means that when we put this into the equation, Kw equals concentration of H plus multiplied by the concentration of OH minus, that means that this value will be a lot smaller. So in conclusion, when you decrease the temperature, then the Kw will decrease as well. Now we're going to look at how to calculate the pH of a strong base. And we can actually work out the pH of strong bases or strong alkalis by using this ionic product of water that we've now found. So we can actually rearrange this formula to find the concentration of H plus ions, because we're always told this Kw value. And so rearranging this gives us that the concentration of H plus ions will be equal to Kw over the concentration of OH minus ions. And so we'll be able to work out the pH. So for this example, find the pH of a 1 times 10 to the power of minus 2 moles per decimeters cubed solution of potassium hydroxide at 298 K. And the Kw is given to us for this temperature as 1 times 10 to the minus 14. And so what we do first is that we see that we've got 1 times 10 to the minus 2 moles per decimeters cubed of this potassium hydroxide. And so we know that the concentration of OH minus ions is equal to this concentration of potassium hydroxide ions. And so it's equal to 1 times 10 to the minus 2 moles per decimeters cubed. And so now we use this rearranged formula of the ionic product of water equation to work out the concentration of H plus ions. And so we have the concentration of H plus ions is equal to the Kw, which is 1 times 10 to the minus 14, divided by 1 times 10 to the minus 2. And that comes out to be 1 times 10 to the minus 12 moles per decimeters cubed. And then we can use the normal pH formula of pH equals minus log to the base 10 of the concentration of H plus ions to work out the pH. So then we get minus log to the base 10 of this 1 times 10 to the minus 12. And so the pH we get is 12.00. And a very important note, so like finding the pH for strong acids, some bases, like calcium hydroxide, will have a concentration of OH minus double the concentration of the actual base. And this is because for 1 mole of calcium hydroxide, we have 2 OH minus ions. So now we're going to look at some questions. So for question 1, work out the pH of these strong bases. So for A, we have 0.75 moles per decimeters cubed of sodium hydroxide. And so what we know is that the concentration of OH minus is equal to the concentration of NaOH, because 1 sodium hydroxide provides 1 OH minus ion. And so we know that the concentration of OH minus is equal to 0.75 moles per decimeters cubed. And then we can work out the concentration of H plus because we know the Kw formula. So we have Kw is equal to the concentration of H plus multiplied by the concentration of OH minus. Now, the concentration, the Kw is normally given to you in the question, and in this case, it's going to be 1 times 10 to the minus 14 like it is for room temperature. And so we have H, the plus concentration is equal to Kw over the concentration of OH minus, and so this is equal to 1 times 10 to the minus 14 over 0.75, and this gives us 1.33 times 10 to the minus 14 moles per decimeters cubed. And so then we can use our pH equation of minus log 10 of the concentration of H plus ions to get that the pH is 13.88. So it's really important to remember that whenever you're finding the pH, you always have to use a concentration of the H plus ions. So make sure you do that. And then for B, we do the same thing. So we have concentration of OH minus ions is equal to 0.04 moles per decimeters cubed. And so the concentration of H plus is equal to 1 times 10 to the minus 14 over 0.04, and this is equal to 2.5 times 10 to the minus 13 moles per decimeters cubed. And then using the pH equation again, we get pH is equal to minus log to the base 10 of 2.5 times 10 to the minus 13, and this equals 12.60. So as you can see, these are both really strong bases, and that's why we use KW.